All right, do Skittles or M&Ms have more orange candies? So Mr. Smith believes that Skittles has a higher proportion of orange than M&Ms, but Mr. Jones believes it's the opposite. So who's correct? So Mr. Smith and Mr. Jones recruited a group of students to help them figure it out. They gave each student a bag of 50 Skittles and a bag of 50 M&Ms. Each student found the difference between proportions, Skittles minus M&Ms, for their bag and plotted the difference on the dot plot. So notice that what we see here are differences. So there can have negative values because some differences can be negative. And notice the direction in which we subtracted. That does matter. Skittles minus M&Ms. So if it's negative, that means there's more M&Ms than Skittles, right, in that certain value. So the first question we always go to is, what does each dot represent in this sample, all right? Well, it is the difference in the proportions of orange candies for one sample of Skittles and one sample of M&Ms. So what we see here is what we would call the sampling distribution, not complete, but it is a sampling distribution of the difference in p hat. So p hat of S minus p hat of M. S for Skittles, M for M&Ms. All right, so from the dot plot, let's make a prediction about the following. On the shape, what do you think the shape looks like? Well, to me, it looks approximately normal based on this box plot. The center or the mean looks like it falls right around somewhere maybe between 0 and 0.02. So somewhere between 0 and 0.02, so we'll just say this, we're just estimating here, 0 or maybe 0.2, somewhere in there. Variability, well, how much variation is between these two? Well, the typical variation between them, I don't know, you could approximately 0.06, but we're just guessing right now. Now, a Google search reveals that 21.6% of Skittles are orange. So P of Skittles is 0.216, the true proportion of Skittles, based on what we know. And 20% of M&Ms are orange. So the true proportion of M&Ms would be 0.2. So now it says, describe the sampling distribution of the sample proportion of orange for Skittles and the sampling distribution and sample proportion of M&Ms for samples of size 50. Justify our answers. All right, so we're going to take the data that we know, the process that we know for one sampling, and apply it to the two sampling. All right, so we're just going to do it in one sample mode right now. All right, so let's deal with Skittles first. Okay, for how would we check for the shape here? Well, we would do large counts test, right? So we would do 50 times 0.216, and then we do 50 times 1 minus 0.216, right? That would give us our large counts test. Well, this gives me 10.8, which is greater than 10, and then the second one gives me 39.2, which is definitely greater than 10. So we know that this is approximately normal. The mean of the sampling distribution, remember the mean of all the p hats is equivalent to the true mean, which would be 0.216. And the standard deviation would be this old formula, 0.216. 1 minus that is 0.784 divided by a sample of 50. That gives me a 0.0582. All right, now we're going to do the same thing, but we're going to do it on the M&Ms side of things. All right, so M&Ms. So 50 times the true proportion of 0.2, that gives me 10, greater than or equal to 10. 50 times 0.8, that gives me 40, which is greater than or equal to 10. So we know this is approximately normal. The mean of all the proportions, the p-hats is equivalent to the true proportion, which they told us is 0.2 based on a Google search. And the standard deviation of a proportion of M&Ms would be 0.2 times 0.8 divided by 50. When I calculate all that, I get 0.0565. Okay, so if we treat them separately, like single proportion samples, we use the same skills we did before. What do we do here? We did large counts. For the mean, we know that the true mean is proportion to, or the mean of the p-hats is equivalent to the mean of the true proportion. And the standard deviation of the distribution is going to be p times 1 minus p over n, right? All that's on your chart. Now, how do we do this when we combine? Well, the sampling distribution of the difference between the proportions, so Skittles minus M&Ms, so they're calling it x minus y. So what do we have to do? Well, it is what you think it is. We would say you would have to check large counts of the two proportions. So like proportion of Skittles, or n times the proportion of Skittles has to be greater than or equal to 10. N times 1 minus the proportion of Skittles has to be greater than or equal to 10. And then what we did with the M&Ms. N times the proportion of M&Ms greater than or equal to 10. And the complement. So we checked both samples. And what did we find? We found that they are both past the large counts test, so we can conclude it's approximately normal. So I'm just going to make a note. We passed on previous page. We showed our work. But we would check large counts. Now the mean of the difference of proportions. So what does that mean? The mean of p hat of Skittles minus p hat of M&Ms is equivalent to the true proportion of Skittles minus the true proportion of M&Ms. So we do 0.216 minus 0.200, and I get 0.016. That's the center we're using in this distribution when we combine them. Now the standard deviations. Way back when in chapter 6 when we combined standard deviations, we talked about, I don't know if you remember this, but it's like the Pythagorean theorem of statistics. You can only add the variances and then take the square root, right? So that's what we're going to do. We're going to find the standard deviation. So I'm going to take the standard deviations that we calculated on the previous page. So the first one came out to be 0.0582, and I square it, and then I add it to the other one squared, so 0.0565 squared. It doesn't matter that they're subtracted, remember, it's always adding when we did that combining variances. So the standard deviation of this combination then is 0.0812. Now that we have the true mean and the standard deviation of this combination, we're just going to use good old norm CDF to help us find what we need to find. So Mr. Smith and Mr. Jones each grabbed a bag and calculated a difference between the proportions of 0.808 from their samples. Calculate the probability of getting this difference or higher. Okay, so if I was drawing my normal curve of the combinations, right? What is in the center? Well, the center is my true mean. We found that difference. And he said he got a sample 0.08. So that's over here. Or higher means it's a right-tailed test. So all I'm going to do is put it in my calculator as norm CDF. Lower boundary would be 0.08. Upper boundary would be what, 10,000? The mean would be the mean we calculated up above, so 0.016, and the standard deviation is what we calculated here at 0.0812. When I run it, I get 0.215. Okay, so there's my probability of getting a sample difference of 8% or more. Okay, not a big deal. That's the general status of how we do this. Now let's summarize. The shape of, okay, so sampling distribution of p hat 1 minus p hat 2. So it's approximately normal if large counts is satisfied. For both. So yes, it's a bit of work, but we can do this. So N1, P1 has to be greater than 10. N1, 1 minus P1 has to be greater than or equal to 10. And then we do the same thing for the second sample. N2, P2 greater than or equal to 10. All right, so tedious, yes, but not a big deal. Now for the center, you are just going to take P1 minus P2. And for variability, it looks like this. Now don't worry, there's some shortcuts along the way that I will help you get to, okay? So notice that we're adding them before we take the square root. That's the variance form of those standard deviations. And then your norm CDF, same idea with the normal calculations, all right? Nothing new under the sun. All right, so if you want to pause the video and try this application by yourself and come back and check it, feel free to do so now. Now let's try this. At Westville High School, there's 315 seniors and 389 juniors. 65% of the seniors have parking passes and 42% of the juniors have parking passes. The stats teacher selects a simple random sample of 30 seniors and separate in a separate SRS of 30 juniors. Let P hat S minus P hat J be the difference in the sample proportion of juniors and seniors that have parking passes. So what is the shape of the sampling distribution? So you guessed it, we're going to have to do these proportions. Now, what did they give us here? So let's make some notes here. So P hat of the seniors is what? 0.65, right? And P hat of juniors is 0.42. Okay, that makes life easier. And notice our sample size is 30. So if I show my work, so 30 times 0.65 gives me 19.5. That's greater than 10. 30 times 0.35, that gives me 10.5. That's just barely, but it is greater than 10. And then I'm going to do the same thing for the juniors. So 30 times 0.42 is 12.6, greater than or equal to 10. 0.58, that gives me 17.4. So we pass. So we know it's approximately normal, and this is our justification, the large counts test. Find the mean of the sampling distribution. Well, we just find the differences, okay? So the P hat of seniors minus the P hat of juniors. Well, 0.65 minus 0.42 gives me 0.23. Calculate and interpret the standard deviation of the sampling distribution. Okay, so we're just going to use that formula. P hat seniors minus P hat juniors. Looks gnarly, kind of is gnarly. So let's do this. So 0.65 times 0.35 all over 30 plus 0.42 times 0.58 all over 30. When I calculate it out, I get 0.1253. Now I need to interpret. So here's our interpretation. So the difference in sample proportions of juniors, or no, I should say seniors first. Seniors minus juniors who have a parking pass. I'll scooch over here. Typically varies by about 0.1253 from the true difference in proportions. Okay? Yes, I abbreviated because I ran out of space. All right, now, what is the probability the difference in the sample proportions of students with parking passes is greater than 30%? Okay, so visualize this. We know our mean is 0.23. 0.30 greater than takes me over here. So I'm going to use my norm CDF. Lower boundary of 0.3. Oops, I need to label. Always label. 0.3. Upper boundary. Something large. All right. The mean was the difference of 0.23 and the standard deviation of 0.1253. When I put that on my calculator, I get something along the lines of 0.2877. Okay? So hopefully you did okay with that example. So this is the general idea of how do we handle it when we do difference in proportions. Now in the next simulation, we're gonna talk about confidence intervals and hypothesis tests. Very similar. Now that we know basically how to check conditions.